morning, everyone. My name is Andrew Fracknoy. I was for many years the instructor of astronomy here at Foothill College in Silicon Valley, and in my retirement, we're still continuing these Silicon Valley astronomy lectures. It's a great pleasure for me to be able to introduce these lectures to you. These are co-sponsored by NASA's Ames Research Center, the Foothill College Astronomy Program here in Los Altos Hills, the Astronomical Society of the Pacific, and the SETI Institute. Tonight's speaker, we're delighted to welcome back Dr. Natalie Battaglia. She is an astrophysicist at NASA's Ames Research Center, and she is the project scientist for NASA's Kepler mission, searching for exoplanets, for planets orbiting other stars. And I think we would all agree this has been one of the most successful and scientifically rewarding missions of all time. So we want to congratulate her on her success. She holds a doctoral degree in astrophysics from the University of California at Santa Cruz. She's been involved with the Kepler mission since the proposal stage and contributed to many different aspects of the science, from studying the stars themselves to detecting and understanding the planets that they harbor. Dr. Battaglia served 10 years as professor of physics and astronomy at San Jose State University before joining NASA Ames for the Kepler project. In 2011, she was awarded a NASA Public Service Medal, and in 2017, Time magazine very appropriately named her to the list of the 100 most influential people in the world. So ladies and gentlemen, please join me in congratulating and welcoming Dr. Natalie Battaglia.
Hello, everybody. Welcome. Thank you so much for the lovely introduction and for having me. It's really a pleasure to be back. It's very meaningful to me because I gave a lecture here when Kepler first was launched, or right thereafter. Then about midway through, I gave an update. And now here I am just 1 month after the Kepler Prime mission actually closed out. So everything, all the ribbons have been tied on the packages and the data's been delivered. And my job is pretty much done. And that feels really great. So I'm here to tell you about the exoplanet science that we did with Kepler. How many of you had heard of Kepler before coming tonight? That's fantastic. Wonderful. So the title of the talk is A Planet for Goldilocks. Primarily because Kepler's reason for existence was to find planets amenable to life, the just right planets. And we'll see that that's not too big, not too small, not too hot, not too cold. And we want to convey the message that the results of Kepler have catalyzed the search for life or evidence of life beyond the solar system in a very tangible way. So I'm going to spend the first half of the talk talking about Kepler results, and then specific to exoplanets. And in the second half, we'll look a little bit towards the future. The search for evidence of life really has 3 pathways, and 2 of them are represented here. On the left, we've got solar system exploration. We have this one example of life in the solar system here on Earth, but that doesn't mean that there couldn't be life elsewhere. The image I've chosen for this to represent this pathway is an image of the satellite of the planet Saturn. This is Enceladus. And what is special about this satellite is that it is seen to have geysers emanating from beneath an icy crust, many kilometers thick. And where there's liquid water, we think that there might be life. So it's very compelling to go searching there underneath the ice and see if any microbes could actually survive in the water that's there. There might also be life in a subsurface cave on Mars, for example. We know that Mars once had water. Maybe it still does today in certain tiny niches. And again, where there's water, we think there might be life. So to go and explore Mars is also very compelling. Maybe we won't find life. Maybe we'll find death in the form of fossils. And I think that's one of the motivations for sending humans there to go and excavate. On the right-hand side, the second pathway is marked by the radio dishes at the Allen Telescope Array up in Lassen near the California-Oregon border. These are telescopes that are listening to the universe for information or for signals that have a lot of information content, that have patterned signals. Too patterned, too regular, too much information content to be explained by regular astrophysics alone, the idea being that perhaps the patterned signals could be due to technology. So those are two of the pathways for searching for the evidence of life beyond Earth. But the third pathway was opened up in 1995 with the first discovery of a planet orbiting another star outside or in the galaxy. And we call these exoplanets, exo being the root for outside of. So all of the planets I'm talking about this evening are not planets in our own solar system. These are planets orbiting other stars in the galaxy. And this is the first, an artist's rendering, not an actual image, but an artist's rendering of what I would consider to be the first discovery of a planet orbiting another star like our own sun. This is 51 Peg B. I won't go into too many details about how this planet was discovered. It was done via the Doppler method, and I can talk about that more during the Q&A. But I want to say that this first planet discovery really surprised us. It wasn't like anything we have in our own solar system. It's a giant planet orbiting about once every 3 days, I think it is, its parent star. So that makes it 10 times closer to its star than Mercury is to our own sun. And in our own solar system, you know, we grew up learning that we've got the small terrestrial planets orbiting close to the sun. We've got the big gas and ice giants orbiting far away, right? So here's a cartoon that shows, a graphic that shows the layout of the solar system planets, where the relative sizes are about right, but not the relative distances. They're all brought in close just for display purposes. But you can see the tiny rocky things close in, and the ice and gas giants far out. Mercury, the one that's closest to the sun here, it would be about 40 solar diameters away from the sun, just to give you some idea. So this first planet, 51 Peg B, was 10 times closer than that. So you can see that it's very hot. And it was a big puzzle as to how a giant planet could form so close. And this very first discovery actually taught us something really important. All the theoretical models say that indeed these planets form farther out, where the temperatures are amenable to creating these gas and ice giants, but that these early solar systems actually are dynamical environments. They can interact with one another gravitationally, they can interact with the disk of material from which they formed, and those gravitational interactions can get them to move around. So when we talk about potentially habitable planets, we have to keep in mind that the planet that we're looking at today through this one snapshot is just a snapshot in time. We have to also consider the entire evolutionary history of that planet. It's part of its story. So that was an important lesson. But the planet 51 Peg B, I think, was also a huge catalyst for that pushed technology towards finding planets that looked much more familiar to us, planets like those in our own solar system. We needed higher sensitivity. And we really wanted to find a planet like Earth, a true Earth-Sun analog. But in order to do that, well, before I talk about that, let's go back to the idea of what actually makes an Earth-like planet, the idea of a Goldilocks world. Today, in terms of the technology that we have, we talk about the Goldilocks planets in terms of their size and their orbits, because those are the two things that we measure. We would love to have more information about these planets, but for now we've got size and orbit. And here I've called that size and energy. Now, why is size important? I've given an example here of Jupiter, Earth, and I think Mercury there over on the far right, or maybe that's Mars. Size is important because while we think all the planets in our solar system have a rocky core, the gas and ice giants have a very thick envelope of hydrogen and helium-rich molecules. Life, certainly hydrogen is important for life, but the other elements that make up life on planet Earth are things like carbon, nitrogen, phosphorus, silicates, right, sulfur, right, in DNA and RNA. So we want access to those heavy elements in order to make complexity grow, right, and to create life. And so on a planet like Jupiter, by the time you get down to the rocky core where you have access to all of those heavy elements, the pressures are going to be too high to create or sustain DNA and RNA, any kind of complex chains of molecules. So those planets are probably not amenable to life. On the opposite side, a planet like Mars is so tiny, the surface gravity is so low, it has trouble hanging on to its atmosphere. And so a planet without an atmosphere is going to have a very low surface pressure, and water is probably not going to be sustainable on the surface. It's not going to be able to pool on the surface and stay there for very long. So we're looking for kind of a sweet spot in terms of a planet about the size of Earth, a range of sizes that encapsulate terrestrial-sized planets. And energy, of course, is this idea that if it's too hot, the water will all be vaporized. If it's too cold, the water will all be locked up in its frozen state. And we need water in its liquid form because liquid water is the solvent that facilitates all of the important chemical reactions for life on planet Earth, no matter how diverse it is. Things like cell transport, metabolisms. So that's what we're looking for. Our Goldilocks world is a planet that is just the right size, not too big, not too small, not too hot, not too cold. Now, in order to find an Earth-Sun analog, we had to find a new methodology for detecting planets. This first planet, 51 Peg b, was detected through this thing called the Doppler method, which is basically looking at motion of the central star and as the planet and star are orbiting one another. And that motion for a planet like 51 Peg b is about the velocity of a car hurtling down the highway. The best our technology can detect is a velocity that's about a walking speed, about 1 meter per second or so, maybe a couple, 1 to 3. But a true Earth-Sun analog is going to induce an orbital motion on its star of something like the speed of a ladybug crawling on the ground. It's very tiny, it's like centimeters per second. Our technology today can't yet do that. So we needed a new technique, and that technique was first proposed in the early 1980s, and it was the transit method of planet detection. And basically, the idea is that is really simple, actually. We're measuring the brightnesses of stars, and we're going to do that very precisely. And what we're looking for are eclipse events, or dimmings of light that happen when a planet in orbit about the star happens to pass directly between the disk of the star and the telescope, right? The planet casts a shadow out into the galaxy. That shadow sweeps across the face of the telescope, and we perceive that or measure that as a momentary dimming of light. It lasts a few hours. It comes back every orbit. And so in this cartoon, you see the cartoon on the top, and then on the bottom, the green trace is actually the brightness measurement as a function of time. That was proposed as a space-based mission 4 times, each time rejected. It was proposed in 92, 94, 96, and 98, and was not accepted as a viable mission for detecting an Earth-Sun analog until the year 2000, actually 2001. But it did become NASA's Kepler mission that was launched from Cape Canaveral on March 7th, 2009. Here you've got a picture on the left of the spacecraft at the clean room at Ball Aerospace. It's a space telescope. The mirror is about 1 meter in diameter. It focuses all of the light directly onto a set of instruments that are very similar to the device you have in your cell phone for taking pictures. Without the color capability, it turns brightness or photons into a voltage. You measure the voltage, you get out a brightness. So very simple design. What makes it complicated is the exquisite precision that's required, and I'll get to that in just one moment. The telescope is actually still up there flying, and it's still taking data. But its science has been divided into 2 parts. The first 4 years was the Kepler Prime mission, and that's the time period for which we collected data to do one very simple experiment. The prime objective of Kepler was to determine the fraction of stars that harbor potentially habitable Earth-sized planets. That is, planets that are the size of Earth and orbiting in the Goldilocks zone. So it's a statistical mission. It was not a mission to go out and find Earth 2.0. It wasn't a mission to find un-Earth analog. It was a mission to take a census of sorts. Or maybe a poll is a better analogy, you know, like you call up 1,000 people and ask them what cereal they eat for breakfast. You apply your observational bias corrections, and then you try and come up with a number that represents the general population. That's basically what we're doing. We're polling about 200,000 stars near the plane of the Milky Way in that yellow, funny shape that's tucked underneath the wing of Cygnus the Swan. And we observed just those stars for a period of 4 years, more or less without blinking, okay? As I said, these dimmings of light only last a few hours, and they're only going to repeat once every year, for example, for a planet like Earth. So if you blink, you can miss it. You want to take that data continuously. And you have to observe a large number of stars because not all of your orbital planes will be aligned so that you get this nice transit geometry, so that you can see these dimmings or have these eclipse events. So all of the science I'm going to be talking about are from the prime mission. There are a bunch of other gray footprints, if you will, going along the sky that represent the other fields of view that have been observed after that first 4 years during what's called the K2 mission. And I just want to distinguish those two. And this is an example of what the data looks like. This is just like the green trace in the animation. We've got brightness measurements on the y-axis versus time on the x-axis. Every white point you see, every white circle is a brightness measurement. You notice a few things. Oh, and this is for a period of 300 days. You'll notice, first of all, there are some black gaps where there are no white circles. So what I said before about the spacecraft not blinking, that's not exactly true. There were some moments in time when the spacecraft stopped taking data momentarily, mostly due to safe mode events. So that's what explains the gaps. You also notice that the white points are kind of scattered up and down. That's measurement uncertainty to some degree. We don't measure the brightnesses perfectly. The stars themselves can also have some intrinsic brightness variability. But what I want to draw your attention to is a sequence of dimmings of light that are periodic over the course of this 300 days. Do you see them? I'll mark them in cyan here for you. There they are. So those dimmings of light occur about once every 45 days, I think it is, and it's due to a planet that's about 2.4 times the size of Earth. So now we're going to zoom in on one of those, here marked in green. So you'll see one dimming of light due to a 2.4 Earth radius planet orbiting at 45 days. There you see it there, just to the left. And if you look carefully, perhaps you'll see another sequence of periodic dimmings of light as well in this actual Kepler data. If not, let me help you with the red lines. Here we are. So those dimmings of light you see are much shallower. That's because the occulting object that is eclipsing the star is much tinier. This object is about the size of an Earth. And it's orbiting once every 20 hours or 0.84 days, which means it's very close to its parent star. So in these two graphics on the left, these are meant to represent stars just like our sun. On the left, I put a black disk that corresponds to a planet the size of a Jupiter. A Jupiter-sized planet removes about 1 part per 100 of the light. So imagine 100 light bulbs, you take away 1. That's the dimming of light you get from a Jupiter. On the right-hand side, the black disk that you can just barely see is due to a planet like Earth. An Earth-like planet is only going to take out 1 part per 10,000 of the light. So the analogy we like to use is to imagine the tallest skyscraper in New York City or downtown San Francisco. Maybe it's got 80 some odd stories. If it's in San Francisco, certainly. All the lights are on, it's nighttime, all the windows are open, and one person goes to the window and lowers the blinds by about 2 centimeters. That's the change in brightness that you have to be able to see. And that's what makes Kepler so technically challenging. You have to demonstrate that the detector technology and the engineering of the telescope is stable enough to give you part per million precision on the brightness measurements. Otherwise, those dimmings of light you saw so clearly with your own eye, without any fancy software, would be obscured by the measurement uncertainty. So just to summarize, how much the starlight dims tells us the size of the planet, and how frequently the dimmings occur, how long it takes to come around once, tells us the orbital period. And the orbital period, according to Johannes Kepler in the 1600s, he taught us that the orbital period is directly related between the separation between the star and the planet. And that's what tells you if it's in the Goldilocks zone or not, okay? All right, so in one graphic, I'm going to summarize Kepler's discoveries. This is a scatter plot with the two measurables that we just talked about: planet radius on the y-axis and planet orbital period on the x-axis. Every dot in the graphic represents a planet discovery. And the planet discoveries that you're looking at right now were all made before Kepler launched out into space. There are some horizontal lines to guide you for relative oh, I'm seeing my numbers are getting cut off. Sorry about that. There's a horizontal line for Jupiter, one for Neptune, and one for Earth, just to guide your eye. You can see that most of the discoveries of planets before Kepler launched were about the size of Jupiter. Indeed, 85% of them were larger than Neptune. So most of the planets' discoveries before Kepler were larger than Neptune. They're color-coded. The blue points were discoveries through the Doppler method, and the pink points were discoveries from ground-based, mostly ground-based transit surveys, like what we plan to do in space, but done from ground-based telescopes. And in fact, we ourselves, here in the Bay Area, built such a robotic observatory right here at Lick Observatory on top of Mount Hamilton. We had a very tiny 4-inch telescope that we roboticized to do this kind of thing and to learn how to do this before Kepler even launched. So that's what the scene looked like before Kepler, and now I'm going to add the yellow points that correspond to Kepler's discoveries. Over the first 4 years, Kepler discovered over 4,000 transiting planet candidates, I'll call them. That catalog is about 90% reliable, so there are astrophysical signals in nature that can mimic a planet transit. That corresponds roughly to about 10% of the sample, and in many regions of parameter space can be even smaller. But of those 4,000, well over 2,000, almost 2,500 Kepler planets have now been confirmed to greater than 99.9% confidence levels. And that's done through other follow-up observations that happen either from the ground or other space-based telescopes, or other analyses with the data that allow us to really nail down the exact characteristics of the planet and know that that is due to a planet. So you can already see some patterns in this diagram. Remember, Kepler is taking a poll, right? So we're doing statistics. We're trying to understand exoplanet demographics. And that's really what distinguishes this lecture tonight from my previous 2 lectures, where we focus mostly on individual discoveries. Tonight, I really get to take a look at the statistics and what they taught us. But you see some patterns. The first, most obvious one to me is that the yellow points are mostly below the Neptune line. Now, over 90% of the planets, well, in Kepler's sample, are smaller than Neptune. So we put a new piece of technology out into space and literally lifted the blinders that were preventing us from seeing the small planets that populate the galaxy. Now we see that they're there in spades. But there are still places where there are no planets. For example, the bottom right-hand corner is pretty much devoid of planets. And that's yet another observational bias. Before, we couldn't see the planets smaller than Neptune. Now we can't see the planets in the very bottom right-hand corner of the diagram. And that's just because Kepler itself has finite sensitivity. But there are other places where you don't see planets. For example, on the left, there's a little desert where there's very few points between Neptune and Jupiter, and that's real. Planets don't like to form there. Planets with those characteristics are extraordinarily rare if they exist at all. And there are physical reasons for that, and our theoreticians are learning from this information and putting that information into their theoretical models in order to fine-tune them. Okay, so we'll come back to this idea of statistics in a bit. Before I go there, though, I'd like to make one point that has been extremely meaningful to me, or at least surprising and informative. What I've learned from Kepler is that the diversity of exoplanets in the galaxy far exceeds the diversity of planets in our own solar system. This has been a surprise to me, and I'd like to just give you a flavor of that. I can't go through all of these discoveries in detail, but what I've done is made a collection of thumbnails of artist renderings that represent very specific planet discoveries. So just to give you a flavor of the kind of diversity I'm talking about, we'll start in the upper left. We have found planets orbiting not normal stars, but dead stars, like white dwarfs, for example. Other teams have also found planets orbiting neutron stars, for example. That's represented in the upper left. We have found planets called lava worlds. These are rocky planets that are orbiting 30 times closer to their star than Mercury is to our own sun. These planets have a star-facing side with temperatures in excess of that required to melt iron. So they've got an entire hemisphere larger than the Pacific Ocean that is an ocean, but it's not an ocean of water. It's an ocean of molten rock, and hence the name lava worlds. You can take that to an even more extreme, and you can put them even closer to their stars, and they begin to literally photodisintegrate. And they show behavior of having a cometary tail. And so you see in the third thumbnail this triangular or cone-shaped darkness that's emanating from the point, just like a comet tail does as a comet approaches the sun. Except here, you know, in the case of a comet, you're talking about a dirty snowball. This is a ball of rock that is doing the same thing. It's being photoevaporated, and we see this because the dimming of light is not perfectly symmetric. It starts off very sharp, and then it comes up very slowly because you've got this asymmetric shape due to the tail. So we see many of those. Down at the bottom, the blue orb that you're looking at is meant to represent ocean worlds. There is a class of planets that has very low density, but they're smaller than Neptune, kind of between an Earth-sized planet and a Neptune-sized planet. So they most likely are covered in a hydrogen and helium-rich envelope like the gas and ice giants, but they're tinier. Moreover, instead of being out at the orbit of Neptune, Jupiter, Saturn, Uranus, you take one of these tiny worlds and you plunk it down at an orbit of like Venus, for example, where it's receiving a lot more energy from its parent star. And so then the big question becomes, what do these worlds do? What are their hydrogen and helium envelopes like? Could it be possible to have a true ocean world where you've got this hydrogen and helium envelope that is partly, at least, in liquid form, completely enveloping the planet? And we really don't know what these worlds are like at all. Next, we've got worlds that are orbiting not one but two stars. So if you were to be on one of these worlds and you look over in the east, you would see not one star rising in the east and setting in the west, but two. And they are gravitationally bound and orbiting one another, continuously switching places, doing a pas de deux across the sky. And taking that to more of an extreme, we find planets orbiting stars in star clusters. These are gravitationally bound conglomerations of hundreds of stars, thousands of stars. So you've got a high density neighborhood of stars. So if you were living on one of those planets, you would look up and see a bejeweled sky, much different than the Milky Way or the starry skyscape overhead. I could go on. There are planets, for example, that are the age of the galaxy itself, that formed around our galaxy's very first stars. That means that the raw materials to build planets were there at the very beginning. And that really fascinates me because I think about worlds where life could get a toehold and have 10 billion years to evolve as opposed to 4.5 billion, and that to me opens up a lot of possibility. Okay, so that's exoplanet diversity, and just to drive home the point one more time about these weird ocean-like worlds, this is a histogram, just a bar chart of all of Kepler's discoveries orbiting certain kinds of stars and out to about an Earth's orbit or 400-day orbital period. So there's that little caveat there on the right-hand side. So on the x-axis, we've just got the planet size, where Earth size would be 1, the number 1 would be the size of Earth. So we've got the brown bars corresponding roughly to terrestrial-sized planets, like Mars and Earth, for example. Then on the right-hand side, you've got the blue bars that correspond to sizes that are roughly like the gas and ice giants, Uranus, Neptune, Jupiter, Saturn. But the most common planet in the Kepler sample is a kind of planet we don't have in our own solar system. These super Earth / sub-Neptune planets at short orbital periods, we don't have one in our own solar system, or at least we think we don't. Maybe the study of the Kuiper Belt objects will tell us otherwise. But for now, we have nothing in that size range. On the top, I've ordered the planets in terms of size just to show you this gap in the radius distribution. And yet that's where most of our discoveries lie. So that to me is very interesting. Okay, but what I've told you already is that we're taking a poll, right? So we've called up 200,000 stars and asked them what planets they have, at least orbiting from an Earth's orbit and inward. And we got our discovery space back. That's what you see here in these histograms. But now I need to transform that into the intrinsic population of planets that's actually out there in the galaxy. And to do that, I need to correct for all my observational biases. In the case of our serial analogy, maybe I made all of our phone calls mostly around 3:30 when all the teens get home, and that biased my results. So I have to think about the kinds of things that bias our statistics, and we have to quantify all of them. One of the biggest biases that we have is that of all the 200,000 stars that we looked at, only a very small fraction will have the right geometric alignment for an eclipse to occur at all. And in fact, the probability of that happening is really small. It can be as small as 1/10 of 1%. At most, maybe 10%. So what that means is, for every one planet we did discover, there are something like 10 to 200 others out there that just didn't have the right geometry. So we make those kinds of corrections. And so when we make those corrections, I can transform a bar graph like this, which is showing the fraction of observed discoveries, into an intrinsic population in the galaxy. And the way I'm going to express that is in the average number of planets per star. So that's what's going to be on the y-axis. And my histogram then looks like this. And I calculated this yesterday. This is with the latest final catalog that was just delivered in June, and with all of our most advanced bells and whistles in order to get the best, most robust measurements. So this is not yet published, so you're seeing it for the first time. But what we've got here again is planet size on the x-axis, the average number of planets per star on the y-axis. And so what you see is that the brown bars, and I've dropped the two to the far left just because I'm not confident about the error bars for Mars-sized planets are really large. So I'm limiting us to Earth-sized planets up to about twice the size of Jupiter. But what we see is that the brown bars came up a lot relative to the blue bars. The blue bars went down, the brown bars came up. That's because my bias corrections inflated those numbers, because the Earth-sized planets are the hardest to find. I had very low sensitivity of the Earth-sized planets relative to the Jupiter-sized planets. So I had to make that adjustment, okay? So this graphic tells me a lot of really interesting things. First, it tells me right off the bat that nature makes small planets more efficiently than large planets, at least inside of an Earth's orbit, or in the inner parts of a solar system. That's true. The other interesting thing I think about this diagram is that if I add up all of the numbers For example, the brown bar is roughly at 0.4. The gray bar, next one over, both of them are around 0.3, 0.3, and you keep going and you add up all those numbers, you end up with a number that's something like 1.3 to 1.5. So what that tells me is that every star, on average, every star has at least one planet. Keep in mind that we're only talking here about planets orbiting within 400 days, in 400-day orbital periods or smaller, and we're excluding all of the Mars and Mercury and Pluto objects out there. I didn't say planets, dwarf planets. So at least one. So when you look up in the sky at night, and I hope that you don't see these pinpoints of lights as just stars anymore. You should see them as planetary systems, because every sun-like star, every normal star has at least one planet. Now, we can take this diagram, and actually ground-based observers have been using the world's best, most powerful telescopes, like the Keck 10-meter telescope, to study all of the stars that Kepler's been observing, especially those that are known to have planets. And they've been doing that in order to pin down their star properties very accurately so that we could know the planet properties with very high accuracy. And if you fold in that information, you get a diagram or a histogram now that looks something like this. So our bar graph now has more bins. So if you follow the orange line from the right-hand side, it starts out very low, around Jupiter sizes, just like our previous bar graph did. And it starts to grow and grow as you get to the Neptune-sized planets around 4, and you work your way into the super-Earths down around 2.5. But then it takes a dive, and it comes down before going back up. And in fact, we did see this in this graphic as well. You see a little dip there in the first gray bar. But now that when we update our star properties, that actually gets more extreme. And what it tells us is that the small planets actually come in 2 different sizes. They seem to bifurcate into 2 different, pile up into 2 different groups. So I wanted to communicate that as an example of the kind of detailed information that exists in that period radius diagram that you saw with those 4,000 points. There are a lot of patterns there. And this kind of information can now be folded into a scenario for developing theoretical models about how planets form. From tiny planetesimals, little pebbles on the left, to rocky cores that then accrete on hydrogen and helium envelopes and that are sculpted and exposed to radiation from their parent star and eventually end up into these kind of 2 regimes of sizes that we call roughly the super-Earths and mini-Neptunes. So we're just beginning to learn what this actually means and what the implications are. I'll come back to that in a minute. But what about the Goldilocks worlds? After all, this is Kepler's reason for existence. Kepler did find Goldilocks planets. This is one example, Kepler 452b, one of the exoplanets most like Earth that Kepler discovered, and it's shown quite clearly in this infographic, this split screen. On the right-hand side, or on the left-hand side, I should say, we've got the sun in the middle. The half disk is the sun, and the Earth in its 365-day orbital period with its size there relative to the other planet, Kepler 452b, on the right. You see that its central host star is very similar to our sun. It's only 10% larger, same temperature, pretty much the same age, a little bit older. It's about 6 billion years instead of 4.5. The planet Kepler 452b is about 60% larger than the Earth. And what we know about planet masses and sizes and densities and compositions tells us that at 60% the size of the Earth, or 1.6, 60% larger than the size of the Earth, we do expect to have roughly a rocky composition. So we believe this is most likely to be a rocky world. It's orbiting its star once every 385 days, very similar to the Earth, which means it's receiving about the same amount of energy. So it makes it a very interesting Goldilocks world. And in fact, Kepler found about 50 Goldilocks worlds, and they're represented in this scatter plot, which is a little different than the period radius diagram I showed you before. Now we're plotting On the x-axis, the energy that's received by the planet out at its orbit from its central star, how warm it is. The green band corresponds roughly to the Goldilocks zone, but you see it's tilted over. That's because the exact numbers for the Goldilocks zone depend on the kind of star that it's orbiting. And so on the y-axis, I've got different kinds of stars. On the top, as indicated by the temperature of the star. Our sun has a temperature of about 5,800 degrees Kelvin, so that corresponds to the biggest circle on the top. And you've got the K-type stars and the tiny M-type stars at the bottom. The details aren't as important as the message here, which is that the 50 Goldilocks worlds that Kepler identified are orbiting a variety of stars, from the tiny M-type stars all the way up to the solar-like stars. And so this offers us a nice sample with which we can do statistics. Again, the point here is to take the discovery space, apply our bias corrections, and turn it into the intrinsic population of planets that's in the galaxy. So to tell you what those results are, I'd like to do a thought experiment. We're going to take the Milky Way galaxy, and we're going to shrink it down to the size of the continental United States, okay? And we're here in California on the coast with our backs to the Pacific Ocean, looking out across the continent, and we're going to ask ourselves the question, based on these 50 discoveries, how far out would I need to look in order to find the nearest potentially habitable Earth-sized planet, okay? And the answer, it turns out to be, if you're here where we are in this theater and you're looking across the continent, where is the nearest potentially habitable exoplanet likely to be? It's right over there on the other side of campus at the Foothill Observatory. It's about 1/4 of a mile away, which is a stone's throw. In galactic terms, that's about 10 light years compared to the 100,000 light years across of the Milky Way galaxy. So when I said at the beginning of this talk that the results that Kepler found have catalyzed the search for life on exoplanets, this is why. We set out to find out if nature makes Earth-like planets efficiently or not. Are they common? Are they rare? We've now found out through Kepler discoveries that there are over 10 billion such planets in our galaxy alone, and the nearest one should be a stone's throw away. And indeed, in 2016, astronomers identified one orbiting not just within 10 light years, but orbiting the very nearest star to the sun, a star called Proxima Centauri. It's in the Alpha Centauri system, which is actually 3 stars, a G-type star like our sun, a K-type star like the middle one in your habitable zone graphic, and a little M-type star. And it's that little M-type star, Proxima, which has a planet that we think is about roughly Earth size and orbiting in its Goldilocks zone. Okay, so that's a look at the Kepler results. I would like to now look a little bit towards the future. And before doing that, you know, at this point in the lecture, you have this new knowledge that there are over 10 billion Earth-sized planets in the galaxy. There are usually 2 responses to that when we start to talk about life. You've got the philosophical camp that says, well, there are over 10 billion planets in our galaxy alone. Surely there must be life. That would be a huge waste of real estate if there was not life on one of them. But then you've got the other camp that's way over on the other side of the spectrum that says, well, but wait a second, life is not just about liquid water. And in fact, we've already talked about some of the things that are required for life, like the right materials. We want rocky planets. And it turns out that you can even take these arguments even further. Well, yeah, you need surface liquid water, but you also need the right kind of atmosphere and a magnetic field to protect us from harmful particles. And you need plate tectonics, because plate tectonics recycles carbon dioxide, which provides us with this great thermostat for keeping the climate stable. And speaking of climate, we need a really stable star. We don't want a star that has a lot of intrinsic variability, and then we don't want a large eccentricity in our orbit either, because that could make seasons so extreme that it wouldn't be amenable to life. And we need a moon to shield us or to stabilize our spin axis. And we need Jupiter out there to protect us from asteroid collisions. And you could go on and on and on. And this is the philosophical camp I'd call the rare earthers. And so when we talk about the prevalence of life in the galaxy, the reality is that we don't have an answer. The answer could be anywhere between these two extremes, and we won't know until we go out and actually measure and look. And so that brings me to the future. Here is NASA's arc of exoplanet missions that are in the works, that have flown, are just finishing, like Kepler, are almost about to launch, like TESS and Webb, or are on the designing, in the design phase, like WFIRST, or are kind of in our minds as ideas, like our future exoplanet missions there on the right. Now what I'd like to say, I want to spend a little bit of time talking about TESS and Webb and look forward to our future exoplanet missions, because we're moving now. You know, we've had 20 years of exoplanet discovery. We had the first 10 years finding planets for the first time, kind of like stamp collecting. We went out and we found worlds and we knew their names. There was Tau Ceti and 51 Peg and HD 1897333, HD 209458. We were stamp collecting. In the second 10 years, we moved from stamp collecting to doing a census or a poll, doing a statistical study in order to understand exoplanet demographics, and that was the era of Kepler. And now we're moving into another phase of exoplanet research, which I want to call atmospheric characterization. We now want to start to learn about the atmospheres of planets. So what I'm showing here is a rainbow. It's a rainbow that stretches so long that I actually have to chop it up and make like an accordion and stack pieces one on top of the other. But it's a spectrum or a rainbow of a star. A spectrum is another word for rainbow. So you see all the colors that this star emits, from red all the way down to indigo. You see some black places, little holes where light is missing. These are absorption lines. These are colors where the atmosphere actually removes light that's emanating from the core of the star. So the atmosphere is taking away those colors so that they don't reach our eye. And it does so in a very systematic way so that these absorption lines, this absence of light, acts as a chemical fingerprint for whatever elements were there in the atmosphere and what temperatures they had and what pressures. So by collecting light from a star, spreading it out into this rainbow, and looking at which colors are missing, we can start to ascertain what's in the atmosphere, you know, what its temperature is, what its pressure profile is, etc. So this is the same thing. This is also a spectrum, but it's represented graphically, not pictorially. So at every color now, instead of showing it pictorially, for every color here, I translate that to a number that's related to an amount of energy that's emitted from that star at that particular color. And I plot those energies as a function of color represented by wavelength. And so here I've got these energy measurements, and you can see the blue trace sometimes dips down. That would be equivalent to a black hole where light is missing. And in this case, these black absences of light are due to particles or molecules like carbon dioxide or methane or water vapor, but that's because this is not the spectrum only of a star. This is the spectrum of starlight that has passed through the atmosphere of a planet. This is a scenario called transmission spectroscopy. These transiting planets are very special, because when they happen to pass directly in front of their star, some of the starlight is going to filter through the limb of that atmosphere, as depicted in this cartoon. Now, this atmosphere is quite exaggerated. This is an actual picture of a planet. It's the only actual picture of a planet that I'm showing tonight. Can you see its atmosphere? It's very difficult to see its atmosphere. I can only see it if I look at the blackness of space on the limb of the sun. This is actually Venus transiting the sun. And if I look there at the limb, I can see a very faint, thin yellow band. That's the atmosphere of Venus. It's only about 5 kilometers thick. So you've got this light that's headed your way toward your telescope from the star, a deluge of light. And only 1 part per 10,000 and 1/200th of that is going to actually have this chemical fingerprint of the planet's atmosphere. But it's exactly that chemical fingerprint that we want to collect so that we can find these kinds of greenhouse gases, maybe even one day indications of a biology that's on the surface and putting metabolic products into the atmosphere. In order to do this, because it's very hard, because it's 1/200th of 1/10,000th, we have to find all the planets that are closest to the solar system. Kepler did a survey. It looked 3,000 light years out into the galaxy, this one yellow cone out into the galaxy, looking at 200,000 stars near the plane of the Milky Way galaxy, and surveyed those stars. So as I said, they stretch all the way out to 3,000 light years. And the ones orbiting the nearest stars were completely missed. There's a future mission called TESS, which is due to launch hopefully next spring of 2018, that's going to survey the entire sky and look for planets orbiting the very nearest systems, out to about 200 light years. Once we find those nearby transit, well, here's a cartoon, an animation of the TESS instrument. As you can see in the barrel of the instrument, you've got 4 black squares representing 4 different cameras, 4 different telescopes, and they're each pointed in a slightly different direction. So TESS, at any given moment in time, can take an image of the sky from the pole almost all the way down to the equator. And it will observe a patch of sky like that for about 28 days or so. Then it's going to clock over and do another longitude strip, etc. It's going to cover first the southern hemisphere sky, and then during the first year, and then it's going to flip and it's going to cover the northern hemisphere sky. And in doing so, it will provide us with targets that have planets orbiting in the transit geometry and are very close to the solar system. And we want the nearby ones just because the stars are brighter, and we get better accuracy of measurements on them. We have a better hope of seeing those atmospheric characteristics. So we want to do that now. We were going to pass these targets on to telescopes like the James Webb Space Telescope. This is the successor to the Hubble Space Telescope. It's going to launch in, well, it was just delayed, something like late summer, early fall of 2019. Or thereabouts. No, maybe it's early summer. Let's say summer of 2019. The date is still uncertain, and it was just slipped by about 6 months. But that's the image here on the left is a mock-up of the James Webb Space Telescope. It's a 6.5 meter aperture mirror. Here's a picture of it in the clean room at Ball Aerospace. There is a human being there that's at about 11 o'clock. You can see him in his white bunny suit. The floor is also white, so he's kind of hard to see. But just to give you a sense of scale, the mirror itself is a segmented mirror made out of beryllium that's very light, mined in Ohio, and coated with a very thin layer of gold, which is highly reflective in the infrared. The telescope was completely assembled, and it was packaged up, and it was shipped to the Johnson Space Center in Houston in the summer. And the reason that it was shipped to Johnson in the summer is because they have there a very large cryovac chamber. And the telescope was inserted into this gigantic chamber with only about 5 inches clearance, so I've been told, in order to simulate space-like conditions. And that means extract all the air to create a vacuum and lower the temperature to make it really, really cold like in space. So they did this. They got it there in the spring of this year. And they had this very complicated timeline for testing the instrument. And you don't need to read all of these words or even understand them. What I wanted to show you, though, is that there are 8 days at the beginning, 7.9 days to create mostly a vacuum inside the cryovac. Then you've got a 33-day period just to get it to cool down to temperature. all right? So that takes already about 40 days total. And then you've got a period of 22 days where the cryovac chamber and the telescope inside is stable enough to do your tests of the instruments inside. And exactly when that period started, around July, Hurricane Harvey made landfall on the coast of Texas, where the Johnson Space Center is located there in Houston. So that was a pins and needles moment. Of course, the major concern was losing power. That would have shot the whole experiment. You'd have to, all 40 days would have been lost. Luckily, they had good generators, but of course, many other concerns, not just for the safety of the employees and their families, their ability to get to work, and once they got to work, the ability to keep them there and to be fed if they were going to actually do their job and probably not be able to get home. Multiple concerns. What ended up happening is that the tests, they did not lose power, the tests went forward, but you can see that they had to be a little creative. They had to put tents over the equipment, the roof was leaking. On the right-hand side, you can see those roof tiles like we have at universities and offices. And they were literally peeling off of the ceiling and dripping onto the floor. So they worked under large duress, but they got everything done, and the schedule, I think in the end, they only ended up losing about 24 hours of time. And all of the instruments checked out beautifully, so that was a huge success. And at the end of it, they were even able to rally and make a hurricane relief crew and go out and help their community. So I think that this is just a wonderful story. And when you see the James Webb Space Telescope launch in 2019 and you start to see the amazing data that comes back from it, I hope you'll remember this story about the human element of the people that made it all possible and the kind of duress that they were under during this stressful time. Okay, now some people say that the James Webb Space Telescope might be able to even detect the atmosphere of an Earth-like planet. I personally think that that's going to be very difficult. Simulations show that we'd have to get very, very lucky in order to do that. We'd have to find an Earth-sized planet orbiting a very, very nearby M-type star like Proxima Centauri, but one that is actually transiting. Proxima Centauri does not appear to be transiting or in that right transit geometry. So we would have to get really lucky. James Webb is going to characterize the atmospheres of many planets, and I actually think that one of its greatest contributions is going to be to figure out what that gray area in between was, between the brown bars and the blue bars, those super-Earth/sub-Neptunes that we have no example of in our own solar system. I think we're going to totally understand what those planets are by observing their atmospheres and seeing what their outgassing products are. We're going to be able to understand their compositions more accurately. But if we really want to find an Earth-Sun analog and look at its atmosphere and see what it's made out of, we're going to do atmospheric characterization in a slightly different way. Instead of focusing on just that thin yellow band that's hugging the planet, that band that's only 5 kilometers thick and is 1/200th of the total area of the occulting planet, we want to catch all the photons that are actually bouncing off of the planet, as shown in this diagram. When starlight bounces off of a planet, just as it does when you look up at the full moon, that starlight is also passing through the atmosphere of the planet. And just like in the spectrum of the star that I showed you, the gases in the atmosphere of the planet are going to eat away some of the colors and produce the same kinds of patterns. But now you've got the entire disk of the planet to work with, not just the thin layer. So you have the possibility of detecting more light that way. It makes it easier. The problem is that planets are literally lost in the glare of their host stars. It's like trying to see a mosquito next to a searchlight. The ratio in brightness between an Earth-like planet and a star like the sun is 10 billion to 1. So in order to make that happen, we have to invent new technologies to suppress the starlight to see the faint things that are nearby. So there are a couple of ways to do this, what's called star suppression technology. The idea is really simple, just like trying to see the features on the ceiling. I can't see them because the spotlight here is in my eyes. But if I put up my thumb, I can block the light and I can see the fainter features nearby. So you can do that by either inserting an occulting disk inside the optical path of your telescope, or you can make a giant occulting disk as another spacecraft that you fly independently of your space telescope. Both ways are being investigated. And I wanted to show you a video, though, of one in particular, just to give you a flavor for what's involved and how difficult it is, because the things that we're trying to see are so exquisitely faint.
A distant star is orbited by two planets. One looks similar to the Earth, the other is a gas giant. When viewed from a distance, the two planets disappear into the glare of their sun. How could we ever find these planets all the way from the Earth? By using a space telescope with a coronagraph to separate starlight from planet light. As the star's light passes through the telescope's large mirrors, it picks up small distortions. Diffraction adds concentric rings to the image we see. To reveal the planets, first a coronagraph uses a mask to block much of the star's light and redirect the remaining light to the outer edges. A washer-shaped device can now block most of the rest of the star's light. Because the planet's light comes in at an angle, it misses the mask and passes through the center of the washer. But when we turn up the image signal by collecting more light, we can see that the planets are still hidden under blobs of leftover starlight. To remove these blobs, the coronagraph has a special deformable mirror that can change shape by using hundreds of tiny pistons. This can correct distortions in the light beam. As the mirror deforms, the blobs of light as seen in the monitor slowly begin disappearing, finally revealing the brighter of the two planets. Afterwards, the fainter planet also comes into view. We can now see objects more than 1 billion times fainter than the star. And if the light from these planets is passed through a prism, we can spread it out into rainbows of color. But some colors are missing. They were absorbed by gases in each planet's atmosphere, giving us important clues about their composition. The search for life in the universe has taken a new step forward.
There's a few ideas that are introduced there, but one in particular is the idea that light bends around obstacles. So when I hold my thumb up to the light, I can't block it out perfectly because some of the light is always going to bend around. So the idea is to shape these masks very, very carefully and to control the wavefront that's coming in very, very carefully in order to be able to really tease out these signals. But this has already been done from ground-based telescopes. A handful of planets have already been identified this way. Not Earth-like planets, not Earth analogs, but planets more like Jupiter, very young Jupiters that are very bright and orbiting at very large distances where the glare of the star doesn't interfere as much. But the point is that technological precursors already exist on ground-based telescopes, and now the idea is to put one into space. So we know what to do, we know how to do it. Technology is almost catching up and at the right readiness levels. There's a 30-year roadmap for NASA. There's a sentence in there which I think is very telling. It says that, "Is there life on other worlds? For the first time in human history, we have finally been able to embark on the systematic scientific pursuit of an answer." And I think that this statement is largely motivated by Kepler's results. I think it's caught the imagination, not just of the scientific community, but also the public, our stakeholders, and our legislators. So much so that in the last Space Act agreement for NASA, the agency as a whole had a 10th objective added to its reason for existence, its purpose. Up until that point, it had only had 9. And as you can imagine, a lot of those are dealing with the International Space Station, manned exploration, etc. But a 10th objective was added, and that is the search for evidence of life beyond Earth. I think that this is achievable within the next 30-ish years, maybe not in my lifetime, but certainly in the lifetime of my children and their children. We're going to be able to point up at a star and say that star has a planet that is a living world, not just a Goldilocks planet, not just a habitable environment, but truly a living world. I look forward to that day. I hope to be alive when it happens. And I hope that in our search for worlds like Earth, we come to appreciate the habitability of our own planet and understand that it's precious, and that creating a sustainable future right here on Earth is worth doing because life is precious. Living worlds are precious. So with that, I'll end on that note, and happy to take your questions. Thank you.
So for the kind of the Kepler 452b, which is kind of a, you said a super Earth, what are the is the kind of probability that there would be a lot of water on some of these worlds? How do we kind of measure with the current technology, without some of the atmospheric kind of light that you're getting through? What's kind of the way of figuring out if they have water, or is there a way to detect the kind of mass and stuff?
Yeah, that's a great question. So how do we figure out, I mean, right now we just know the size and the orbital period, so we can get a measure of how much energy is being radiated onto the surface of the planet, but we don't have any idea of what the atmosphere is actually made out of. And until we know that, we can't ascertain whether or not liquid water could actually pool on the surface. I think that, well, I don't know what we're going to find. Certainly if the pressure and temperature is right, and if there's water vapor in the atmosphere, you can pretty much be certain that there's going to be water vapor on the surface, or water pooling on the surface in the form of an ocean or lakes or something on the surface. Barring, I mean, that's how we want to find out if a planet is truly a habitable environment, whether it has liquid water on the surface. I mean, there are a couple of other ways. Some people have suggested that you might be able to perceive the glint of starlight as it's reflecting off of a sheer water surface like an ocean. You can also look at the reflectivity of light. For example, light reflects differently off water than it does off of rock or desert or forest or ice. This is a property called the albedo. And if you look as a planet rotates and it presents different faces to you, you might be able to see different amounts of reflected light coming back to your telescope. And maybe that will be another way to disentangle whether or not there's surface liquid water. Yeah. Over here, yes.
Thank you for your wonderful talk and wonderful research that makes it seem more likely than ever that there are Earth-like planets. And that brings up in my mind the Fermi paradox. And I just wondered if you had a few thoughts on a resolution to that. For those who aren't familiar with it, it's basically...
There's a funny echo in here.
Oh, I'm sorry. Did you hear what I said?
I didn't catch it. Did you?
Oh, okay.
Repeat the question, please?
Well, I just said, thanks for your research that suggests there are, lots of extra, Earth-like worlds out there. And that brings up in my mind the Fermi paradox, which, where are they if there are, say, people out there, intelligent extraterrestrial life? And I'd just be interested in your thoughts on the resolution for that.
Well, I don't have an answer to the Fermi paradox, but to me the Fermi paradox says that maybe space interstellar travel is difficult. It doesn't necessarily speak to whether or not living worlds are common or rare. So I don't know. We won't know the answer until we go out and search. I mean, the Fermi paradox is, as he said, where is everybody? If life is indeed very common, how come we haven't seen any indication of other life in the universe? To me, that presupposes that life would somehow come here or make itself known to us. We'd have started these systematic surveys of, like the SETI surveys have gone out and listened, but have so far probed just a tiny part of the parameter space that's out there. So we haven't done a complete survey, so it's not fair to say where is everybody until you've actually done a systematic look.
Hi.
Yes.
Given that the James Webb telescope is essentially built at this point, can you give us a sense of what work is left in the next year and a half, 2 years, to get us to launch?
I'm not sure I understood the question. So the telescope is almost ready.
It's almost ready, so I'm curious what else is left.
What else
next
is left?
year.
Yeah, it's so underneath the telescope is a tennis court-sized structure that insulates the telescope and keeps it protected from heat. And so that is what's being assembled now at Northrop Grumman in Southern California. And that process is taking a little more time than they thought it would. That's the sun shield. So that's, I think, what was responsible for the delay. But the spacecraft was actually, the launch was probably going to be delayed anyway because of a European mission called Bepi Colombo, which is a solar system exploration mission to Mercury that was also had a launch window of October 2018, which was the initial JWST launch window. So unless that mission changed its timeline drastically, we would have had to move anyway. So I think NASA was just preemptive and said, oh, we'll just go ahead and move. Yeah. Let's see, over here? Yes?
What happens when you find a perfect Goldilocks planet?
I'm really having trouble making out the words.
What happens when you find a Goldilocks planet?
What happens when you find a Goldilocks planet?
When you find a perfect one, the one that you want.
What happens when we find an Earth-like planet? So one that we know has life on it? Well, that's a really good question. What do we do? I think that we're going to want to find not just one, but a lot of them. We're going to want to understand the diversity of planets out there. And we're going to need to learn a lot before we think about actually going to these places. But I do think that once we have the stars, if you can point to a star and you say that star has a living world, I think that humans in their creativity and sheer will are going to figure out a way to get there. And a little bit of that is already happening. They're trying to build very, very tiny postage stamp-sized spacecraft to go to Alpha Centauri, for example. So I think that we'll eventually want to go there, but I think humans have a lot to learn before we go and mess up other planets, so I'm hoping it kind of takes a long time. I think that we should do that carefully. You know, in the past, when we went exploring, we made a big mess of things, and I think that we can learn from our mistakes and maybe not make such a mess of things next time. Yes?
Hi, thank you for your lecture today. This stuff is just utterly fascinating and it's just so inspirational to me, and I would love to be a part of the mission. And this question isn't about the science or the talk today, but I want to know, I'm a student here and I'm a chemical engineering major, and I would love to know what would be my educational plan, what would be my career path in order to be a part of this.
Yeah, that's a great question. You know, for everything from art to science and engineering, these missions employ people that run the gamut. We have artists who do the artist renderings, who get all of the information about these worlds, everything that the scientist knows, and makes them come to life. Writers, we've got writers. The search for life is interdisciplinary, so it requires planetary scientists, geologists, atmospheric scientists, biologists to understand the biology, and astronomers. And then you've got all the engineers. So I think that there's so many different ways that you can contribute and be a part of it, just to study what you love, to do it, to expose yourself to lots of different things, and to always have an open mind and take risks, and just do it. You know, I mean, that's what I did. Take a lot of math and science, do well at it, excel at it, but you know, even if you don't do well at it, keep at it, because nobody is good at it at the beginning. It's a new way of thinking. You have to train your brain to think in that new way. I certainly wasn't good at it at first, but you keep at it, your persistence, because that's what it needs to make these kinds of things happen, is just sheer persistence. And you're in a great place for all of this. This is, yeah. Yes?
Thanks for your very informative presentation. I really loved it. So this question is related to the Starshot technology suggested by Stephen Hawking, where you propel a particular nano satellite using laser towards a particular star. So do you think propelling them towards Proxima Centauri or Alpha Centauri will actually bring in some information and we could actually find an exoplanet like Earth there?
Well, we already know that there's one orbiting Proxima Centauri. So the question is, you know, if you're going to send just one object out there, you're going to have to choose between them. I think that the fact that Alpha Centauri is a triple star system, the statistics for the potentially habitable planets basically is turning out to be about 25%. So that means 1 out of every 4 stars is expected to have a potentially habitable Earth-sized planet. So the Alpha Centauri system has 3, so you have pretty good, pretty decent odds. In fact, the 25% is for a narrower range of the habitable zone. If you look at the full habitable zone, it's actually probably more like 30%. Well, and if you go down to planets that are smaller than Earth, that number is probably more like 50%. So that gives you a pretty good chance that you're going to find something interesting. Yeah. You know, there are other missions that are proposed to do this kind of direct imaging star suppression technology using a small telescope only pointed at Alpha Centauri, Alpha and Beta Centauri. That has not, well, it was proposed once to NASA already and it was not selected. And I think NASA in general sees it as being too risky because you don't have a guarantee of a scientific result. I personally think that's short-sighted because even if the Alpha Centauri system does not have a potentially habitable Earth-sized planet around A and B, I think that's a scientific result in and of itself. So I don't know, I don't understand that rationale. But your question is specific to Starshot. I'm not exactly sure what you're asking. Is it a good idea or do you have a more specific question about Starshot in general?
So my question is, if we do plan to send something like that, can we point it to that specific planet and maybe explore the atmosphere or something like that?
Oh.
And can we actually
I mean, could you actually do science with Starshot? I mean, Starshot is this postage stamp-sized spacecraft that I was mentioning earlier. In order to study atmospheres, you would need to have the capability to detect light, to measure it, actually to spread it out into a spectrum, and to measure those energies at all those different colors with very high precision. Then you have to be able to transmit that data back to Earth. So that's a lot of instrumentation, and spectrographs tend to be very large instruments. You're not going to fit it on a postage stamp-sized object. But it should, the idea is that it would be capable of taking pictures. You know, send a cell phone out into space, or I mean, Starshot is even tinier. But the idea is just to go out and take pictures. And so, yeah, you should be able to at least be able to detect its presence. Yes.
Okay, next question. So, based on your data, did you observe some kind of patterns or equations that can predict planets in certain places, like, for example, TTS Goldilocks? Don't you know what I mean?
I am having, it's the echo. I can't understand the questions.
For example, what? I mean, did you find a way to mathematically predict if there is a planet somewhere based on the planets you already observed? Like
yeah, can you make a prediction about whether or not a star is going to have a planet based on the statistics? I mean, you can only make a probabilistic, with the statistics, with the demographic survey, you can make a probabilistic argument. You know, for example, around Alpha Centauri A and B, based on the Kepler results, I can guess, I can quantify the probability of about 75% that we would find a potentially habitable Earth-sized planet around those 2 stars, one of those 2 stars. So I can make a probabilistic argument, but I don't know of a way to make a definitive argument that would be a yes or no gate that's very clear.
My point is that, for example, in the solar system, there is already some pattern in the distance between the planets, and their location, this TTS for the hypothesis. Did you observe something similar in other systems?
So he's asking if there's a similarity between the architectures of planetary systems that would help us to make predictions. That's a great idea. What we've learned from architectures of planetary systems is that they too are more diverse. They're not all like the solar system. For example, one of the reasons why Kepler found 4,000 planet candidates is because we've got a lot of multiple planet systems. But more specifically, these systems can have 6 planets orbiting all interior to what would be Venus in our own solar system. We call these dynamically compact systems. 6 planets orbiting interior to what would be Venus in our own. And they tend to have very specific characteristics. We know that our own solar system planets orbit along a disk, for example. You can think of that like a pancake. These systems, the dynamically compact systems, are so exquisitely coplanar that they're more like crepes as opposed to pancakes. They're just really exquisitely coplanar. So there is some physical characteristic about them that distinguishes them from a solar system architecture. All that tells me is that the architectures are diverse. So I'm not sure that there's predictive power there, but who knows?
Thank you, Natalie, for this intellectually stimulating talk. My observation about the scatter plot, where you showed like I guess the size of the planet on one axis, and then on the other axis, like the period.
Yes.
Is that the area right around like 1 Earth radius and 365 days for our Earth year? That area looked particularly empty to me.
Yeah.
I think I only saw like 1 or 2 points kind of right in that area. And then a few slides later, when you showed that slide comparing Earth on the left with, I guess, an Earth-like planet in the Goldilocks zone on the right, that one was actually 1.6 Earths. So
right.
I'm just wondering, is the the exact kind of replica of Earth, like 1 Earth radii in 365 days, give or take a small factor, is that particular configuration especially rare? Because it looked like there was a gap there in the chart that you
Yeah, that's a great question. So our numbers of detections of exact Earth-Sun analogs is really, really tiny. And we have more detections above 1.4. So on the period radius diagram that I showed, that scatter plot, both axes were logarithmic, so it tends to exaggerate the effect. If you go up quite a bit off of the Earth radius line, you're still kind of in the regime of a rocky planet, so it's a little misleading. But you're absolutely right. The numbers of discoveries there are really, really small. And that's because those are the planets that are hardest to detect. We're right on the envelope of what Kepler is capable of. To the bottom right-hand side of that line, we have 0 detections. That's because that's where our sensitivity falls off. So we didn't over-design the engineering of this instrument to be able to do sufficiently beyond. What actually ended up happening is if Kepler observed stars that behaved exactly like our sun, we would have detected about 10 such planets that are kind of Earth-Sun analogs, about 1 Earth radius. But it turned out that the sun was quieter than the average G-type star that we observed. So there's a little more intrinsic variability of the stars compared to our sun. And that just added a slight noise component that made it more difficult than we thought it was going to be to detect those planets in that part of the diagram. So what we wanted to do was to continue observing those stars for another 4 years. But then one of Kepler's reaction wheels failed and we couldn't do that. We had to move to different parts of the galaxy. So we kind of thought that we were only going to be sensitive to planets that were about twice the size of the Earth in that 365-day orbital period range. But the very innovative, bright engineers that designed the software found ways to improve the pipeline to be more sensitive. So we ended up recovering a little bit of the sensitivity that we lost because the stars were more noisy than we thought they were going to be. So I'm very, very happy with what we accomplished in that we found these 50 Goldilocks worlds, and some of them, albeit small numbers, are orbiting even the sun-like stars.
And will there be an initiative to get to that one-to-one?
You need to let other people.
Oh, okay, all right.
And I'm going to give 3 more.
Three, okay, we were told 3 more, and I see 6 people standing. Okay, well, we're back on this side.
Thank you for a great presentation. This is wonderful.
You're very welcome.
I have a question about current capabilities that you have. And there were some announcements about exomoons discovery. And are we close to be able to discover actually if they are co-orbiting together and if they are transiting to see the two dips and basically detect the larger exomoons of exoplanet?
Yeah, so the idea is that, and I should mention, we found 50 Goldilocks worlds that have roughly terrestrial size diameters, but there are hundreds of Goldilocks worlds that are larger planets. And the idea is, well, what if those larger, maybe gas and ice giant planets have satellites that are roughly Earth-sized, kind of like the Pandora scenario in the movie Avatar? So there are researchers who have been combing Kepler data quite carefully in order to look for other dips of light nearby a primary transit to see if there's evidence of a satellite. And so far, it hasn't returned anything definitive. However, a statistical look at the data has shown that there does seem to be some transits that have a slightly perturbed shape that could be indicative of something. Those objects are being observed with the Hubble Space Telescope, like pretty much right now. So it's not a done deal. Kepler might yet yield the discovery of an exomoon. We'll have to wait and see. Yeah. Let's see, one over here, and then we've got a child over here that would like to ask a question. Yes?
So in your talk, you're defining habitability based on Earth and current age of the solar system. But I guess solar system is also evolving. So maybe in previous couple of billion years ago, we had maybe life in other places that we are not knowledgeable right now. So do you take that into account when you're looking into
the evolution of the solar system
like
and
other star systems, because their age might be different from our side.
Yeah, absolutely. This is a really important point because our atmosphere right now looks the way it has had this oxygen content for a relatively short amount of time. If we look at a planet in its first 2 billion years of evolution, we would probably conclude, and if it were like Earth, we would probably conclude that it was a lifeless world, because the kinds of creatures that populated early Earth didn't create sizable quantities of oxygen. I mean, they were putting oxygen into the atmosphere, but the oxygen was being leached out of the atmosphere at a relatively constant rate. And so it took a long time for the oxygen to accumulate in the atmosphere to reach a saturation level and then continue to grow. So we recognize that that's a problem, and it's going to factor into the detectability of living worlds. We have to take that into consideration. I don't know what we're going to find. I mean, we have to, you know, there's a lot of arguments for when we do design. Right now, people are behind closed doors deciding how big the telescope is going to be to find life, to find living worlds. And I'm arguing that that telescope should be at least 16 meters in aperture. It's about the biggest thing that we can fit into a rocket fairing. And honestly, I think that we could assemble telescopes in space if we had to. I would not argue for going smaller for exactly these reasons, right? That there's a lot of things that could actually make it difficult to find life. And I don't want to be in a position where we have a null result and we don't know how to interpret it. So I would like to be able to find at least 3 dozen nearby potentially habitable planets in the Goldilocks zone and image them and look statistically at their atmospheres in order to get a better feeling for how they differ. Yeah. Yes?
So if the Kepler is orbiting the Earth, how does it keep looking at one point in the sky all the time?
You're going to be an engineer, right? It doesn't orbit the Earth. It's actually orbiting the sun. So what that means is, you've got the spacecraft here, and it's always got to look at the same part of sky, right? And so it's orbiting not the Earth, but the sun. So sometimes it's going to be pointed kind of over the sun. And that was one of the constraints for where we could look in the sky, because we couldn't look at a place in the sky where once in orbit, the telescope would be pointed towards the sun. We had to be pointed away from the sun. But yeah, it's because it's not orbiting the Earth, it's orbiting the sun.